All right, so we're going to finish off magnetic theory with the idea of domain theory, which essentially is going to give us a way of envisaging what's going on at the small level inside of a magnet. So to get there, we start with the idea of, well, what are the elements on the periodic table that can be attracted to a magnet? And there are four. We have iron, nickel, and cobalt, which are, in terms of our periodic table, all right here in the middle. And then we've also got gadolinium, which is this guy down here. Each one of them, as you might remember from our video yesterday, is close to or exactly with a half full outer electron shell. And that allows it to be magnetic. Some of the heavier ones here, so when we get to these guys up here, fairly lightweight. This one is fairly heavyweight, but it's got its outermost electron shell. It's got a new, different electron shell from some of these other ones. More on that in chemistry, actually. But they are half full or very close to half full shells, and that's going to help to explain their magnetic properties. We call these types of materials, in fact, ferromagnetic. Ferro actually coming from the word for iron, because initially it was thought that it was just iron, and then we kind of expanded that to cobalt and nickel, and eventually gadolinium. Anyways. Question might be, though, like, why is a piece of unmagnetized iron or cobalt or nickel or whatever, why do they get attracted to a magnet? I mean, normally I can have a bunch of paper clips and I jumble them together and they really have no effect on each other unless they loop through each other. I guess I can pick them up that way. But they normally behave as if they are not magnets. So when you bring them close to a magnet, they are attracted to the magnet and then also to each other. I'm sure at some point as a kid you played with, a magnet and some paper clips, and you could make the magnet pick up one paper clip and then make a string of them that are all attached to each other. And these materials that initially were not magnets now have suddenly become magnets, and we might wonder, why is that? And the idea is explained using the concept of magnetic domains. And ferromagnetic materials are composed of tiny, we call them domains. And these are basically about 1 micrometer in size. So if you imagine size-wise here, definitely not as big as this. We're imagining them to be this big. But 1 micrometer is 1,000th of a millimeter. So if we were to divide a millimeter into 1,000 pieces, that's the size of these guys. All right, so we can also represent these domains as arrows pointing towards the north, almost like our little test magnets that we were talking about. But here, indeed, they are these little magnetic domains inside a piece of magnetic material. Again, thinking back to the video from yesterday, this is like those little chunks of the material with all of the soldiers wearing the different colored uniform things. I'll put the link to that video in the description for this one. So if I look at a piece of unmagnetized ferromagnetic material, its domains are random. More or less, they're pointing in every which direction, and the magnetic fields cancel each other out. So the net magnetism is 0. All right, so B equals 0 if we were to take the sum of all B, right? So if we want to be very mathematical, it's like sigma B equals 0. We've got some pointing up, some pointing down, some pointing into the screen, some pointing out, some pointing left, some pointing right. And all told, they're going to be equal to 0 or very, very close. And so there's no noticeable magnetism in this unmagnetized ferromagnetic material. Which is why ferromagnetic material normally has no real effect on each other. They have no net magnetic field. However, if we bring a ferromagnetic material near to a strong magnet, all of the domains get affected. But how? Okay, we can say they do, but okay, tell me how. Well, first, the magnet is going to create a magnetic field around and through the material. You think, okay, what direction is this external magnetic field? Again, we think back to our little test compass, and of course, the magnetic field faces away from the north end of our permanent magnet here. So drawing it out, it's going to look something like this. Magnetic field goes away from north and towards the south. To see what this does to the material, instead of looking at all of the arrows there, let's look at just one. Well, what is this magnetic field going to do to the domain? Well, it's going to repel the north and attract the south, which means this domain is going to rotate. Right? It's going to rotate until north is facing directly away from the north pole of the magnet and south is facing towards it. So we're going to get something like this. Right? Magnetic force is going to push north away and pull south towards. And it's going to rotate until we're finally left with something like this. And as a result, the domains are going to align in the same direction as that external magnetic field. All right, so right, dead center away from this, of course, it's a nice straight line this way. Let's pretend this is a straight line and not squiggly like my mouse is drawing it. Away we go. And so now the material has become magnetized. Any magnetized material has, let me try that again. Any magnetized material has all of its domains that are aligned. So you can see the picture here, kind of imagining what those domains look like after it's been magnetized. Right? The magnet has induced the opposite pole in the material, which means all of the north domains are pointing away, all the south parts of the domains are pointing towards the north end of my bar magnet, which means this material, piece of metal that formerly was not magnetic, is now attracted to the magnet. Now, this process does not take a long time to come up with, so it's not like we're sitting there waiting for this to happen as you try to stick a magnet on a fridge or something like that. It goes real quick. And now that this material has been magnetized, it has the ability to do essentially the same thing to other ferromagnetic objects. So, right, one paperclip becomes magnetized, all of its domains align. They're now having an external magnetic field that they are exerting on the outside of them, which is going to make other ones align to it, and so on. Which explains why they are attracted to the magnet, as well as to each other. When we talk about ferromagnetic materials, we have to talk a little bit on how easily they gain or lose their magnetism. So we classify them as either soft ferromagnetic materials or hard ferromagnetic materials. Now, this soft and hard is sort of misleading. It's soft as in easily lost, easily gained, hard as neither easily lost nor easily gained. Not soft as in this one's like a pillow and this one is like a concrete block. So just be careful with that. So soft ferromagnetic materials are pure ferromagnetic materials. Pure iron, pure nickel, pure cobalt, pure gadolinium. These things quickly gain or lose their magnetism. Unmagnetized iron, again, random domains, net B equals 0, right? B net equals 0. Natural state for iron is unmagnetized. when we bathe that iron in an external magnetic field, all of its domains align easily, even for small magnets. Since all of the domains align, it becomes a very strong magnet. Right? However, if we remove the external magnet, iron returns to its natural state very quickly. It quickly demagnetizes. There's nothing really holding all of those domains in an ordered fashion. So soft ferromagnetic materials become very strong magnets, and they're excellent temporary magnets. So if we want to make a nice electromagnet, right, you want to turn the device on and off quickly, soft iron core is excellent for that core, because that's going to be able to become magnetic when we want it to be, and quickly shut off when we've picked up whatever we wanted to pick up and need to drop it now. All right, hard ferromagnetic materials are alloys. Okay, and so these, again, if you think back to like grade 8 and grade 9 science, maybe even grade 10 a little bit, these are alloys which are mixtures of solids. Normally they're mixed when they're in the liquid form. There's not really any chemical bonding that takes place between them. But we're combining here ferromagnetic and non-ferromagnetic materials. Often bar magnets are made of some alloy of iron, aluminum, and carbon, or aluminum, nickel, and cobalt. All right. The non-ferromagnetic material that's mixed in with that acts sort of like cement, and it holds the domains in position, which means it takes a while for this hard ferromagnetic material to become a magnet, but it also will lose its magnetism quite slowly as well. All right, so again, unmagnetized iron, aluminum, carbon. Random domains, B net equals 0, natural state. Right? If I bathe this in an external magnetic field, some of the domains align and it becomes a weak magnet. Magnetic field is not strong enough to overcome the quote-unquote cement for most of them, because we've got lots of the non-ferromagnetic stuff that is holding them all in place. All right. Now, if we bathe that iron, aluminum, carbon in a very strong external magnetic field, most of its domains will align. We've created a strong magnet because most of the domains are now doing what they're supposed to. And because we've got the non-ferromagnetic material there, that cement, the non-ferromagnetic material, helps to keep the domains doing what they're supposed to, which means our iron, aluminum, carbon alloy becomes magnetized, and now we've got a bar magnet. Bend it around, becomes a horseshoe. Advantages here is that they are great as long-term magnets. So if you have a device that requires a constant magnet, you want a hard ferromagnetic material. Now, these are not perfectly permanent magnets, though. If we heat them, or shake them, or smack them with a hammer, the cement, if you will, is loosened, right? So those non-ferromagnetic materials, they get moved enough that they stop holding the domains in place, and the domains start to return to their natural positions. Bar magnet becomes unmagnetized. Basic thing here is the heat or hitting it or shaking it makes particles move. It's really no different than what happens when you heat something. Well, the particles start moving faster. When these domains start moving faster, they tend towards randomness. They become unaligned, and our bar magnet becomes unmagnetized, or at least a weaker magnet. So we could say, okay, using domain theory, explain why a magnet sticks to a fridge door. So I've got a magnet, North Pole, South Pole, moving it towards the fridge door. All right. The fridge door now has to be ferromagnetic for this to work. Usually they start off unmagnetized, which means its domains are random. Move my magnet close to it. So let's imagine I'm moving the south end of the magnet close to the fridge. That means my external magnetic field is pointing towards. And now what's going to happen here? We're bathing the door in an external magnetic field. The domains nearest the magnet align, and they align in the same direction, which means these domains here that are close to it, bathed in this external field, the north end is going to be pointing towards the south end of the magnet. They are attracted to each other, and the magnet sticks to the fridge. Induces the opposite pull in the fridge, which is close to the magnet. Opposites attract. Again, magnet sticks to the fridge. Right? You have an assignment to do in your workbook, and once that's done, there is also a skill check. It's only 3 questions, but it is curve straightening, so there's going to be some graphing stuff there. Additionally, if you have not finished the previous day's work, that is something that you could at least look at doing some of. It's not for marks specifically, but you could do some of that to prepare you for the skill check. Thank you.